There we go. So we're going to break this up into several YouTube segments. So occasionally I have to hit stop and then start again. Many of you asked for me to write a review, basically a guide to all the stuff you need to know in one place, but rather than a 50-page textbook chapter, turns out to be like 7 pages. There are no examples. All of that you can find somewhere else in recitation. Um, it's just the basic principles of physics for conservation of momentum, the work energy theorem, um, and conservation of energy. Uh, if you would like to see that, it's linked from the main course website. I also sent it out by email. I hope that's useful to you. So last week I told you all that I would make something like that. I have finally finished making it, so it's online. Your homework set is due tomorrow by the end of the day. Your next homework set, which is going to be shorter, will be posted at the end of the day on Wednesday. This is going to be probably 5 questions. I haven't written it yet, but I think I know what the questions will be. There was no pre-lecture question today, so you didn't miss anything. Yes, Samantha, it'll be due before the exam, and it's kind of designed as a practice for the exam thing. Where will the slides with my notes be posted? On the course website and on Blackboard. So as soon as I'm done scribbling on this, I have a little button in my program. You can't see it here. It doesn't pop up the menu, but I have an export as PDF button, which I will push and then send this out. So after today, we are done with new material for exam 3. So today is a little bit of new material, although in 9:30 we spent most of it on review. Thursday is going to be half new material and half review, but new material that is not for exam 3. New material on the philosophy of science, which will be important for our paper. My clinic hours today have changed. I was originally going to be in the clinic from 2 to 4 today, but I have to cover another professor's class who is at home and sick. So I'm going to be teaching up until 2, and I would like a lunch break. So I'm going to take a break from 2 to 3 and then be in the clinic from 3 to 4:30. When is the paper being assigned? It will be assigned likely Thursday. I may refine the assignment, but the real posting will be next. You'll have all the material for the paper next Thursday. So your exam will be next Tuesday. Next Thursday, we'll talk in depth about what the paper is about. So really, the paper is going to be assigned next Thursday. But I can give you a preview of it this Thursday. Today, I want to answer your questions. I want to do some demo problems on conservation of momentum and energy. It turns out conservation of energy is the thing everyone wants to talk about. And when I say conservation of energy, I also mean the work energy theorem. And then we're going to meet a new idea, which is power, and look at an example of that idea of a cyclist riding up and down hills. So that's the plan for today. We ran a little bit behind schedule in 9:30. I still have time for all of your questions. We spent a lot of time talking about the homework, but I'm going to try to go a little bit faster this time. But if there's ever something that you're not clear on, please type in chat and I will immediately drop what I am doing and take your question. So first off, I want to give you all a chance to ask questions about homework problems, recitation problems, or big ideas, things you'd like me to review. While you're getting out your homework PDFs and thinking about what you want to do, some of you have seen that I am posting YouTube videos of literally everything. So the lectures are of course recorded and put on YouTube and Bilibili, but so are solutions to your homework, solutions to the recitation problems. Everything that we do in class, I am trying to record like me solving the problems in real time on this tablet and posting a video of that along with my thought process in solving them. So let me know how useful those are. And if you'd like, give me some feedback in chat. This gives us something to do while everyone's fishing out their homework. Sarah asks, for homework questions 4 to 7, do we need to solve them as well or just set up those equations? We would like you to take a crack at solving them. As a warning, on problem 7, um, especially 4 through 6, we want you to actually solve them. Like actually do the math, actually get a number, and see if it makes sense. Because as engineers, you're going to have to do numerical calculations or program a computer to do them. For problem 7, we want you to take a crack at the algebra for this one as well. This algebra is disgusting. Um, I said earlier in the semester that there was a particular homework problem that would be the grossest algebra you'd have all semester. This was the problem with a hiker towing the sled behind her. Um, Professor Rudolph wrote this question and he kind of slipped some gross algebra past me. Um, so I am sorry. We want you to take a stab at this algebra. It's important that you see disgusting algebra and kind of understand some techniques for solving it. But for problem 7 on the homework, if you're unable to get the algebra crunched through, um, don't sweat it. It's not going to mess up your grade. You can just say, I would solve this equation for this variable, or these two equations for these two variables. Okay, for the multiple choice, most people are saying that the videos are useful. Some people are saying that they haven't watched them yet. So for people who answered D, some of your classmates say that have answered C and say that these things are useful. So take a stab at that. It's all posted under videos on the course website. And there's a YouTube channel so you can get from one thing to the next. We have a student who's posting everything on Bilibili as well, but I'm not sure how channels on Bilibili work, but all the links are on the website. So, so Jasmine says, general question, I'm still a little conserved on the terminology of conservative versus non-conservative forces, external forces, and also mechanical energy. Could we briefly go over what each one means in which case and type of problem we might see each? Yes, absolutely, Jasmine. The energy stuff, I have an example designed to go over exactly that coming up in like 3 slides. So all of the stuff on energy, I will talk about kind of in the context of the problem I've prepared to talk about them in. But if after we do that, if you're still unsure about that, please ask again. I want to touch base with you after we do that problem just to make sure that you've got that. But in asking about external forces, let's talk about the conservation of momentum. So the conservation of momentum, if you remember where we started, was we said that we started with Newton's third law that says that if two objects push on each other, their forces are equal and opposite. So that means that their mass times acceleration, whoops, is equal and opposite. Mass isn't a vector. What am I doing? Blurp. So that means that since acceleration is just a change in velocity over time, that their changes in momenta are equal and opposite. So the change in momentum of one thing is equal and opposite to the change in momentum of the other thing. But, so this is conservation of momentum, right? But we got here by assuming that the only forces were the ones that those objects exerted on each other. if you have some other force coming from outside, then um, that's not true anymore. And the assumption breaks down, and we can't use the conservation of momentum unless we also think about the thing on the other end of that force. So, for instance, if I have someone like pulling a box from off camera, like there's a rope, and you don't know what's on the other end of the rope, but you know its tension is 100 newtons, you can't use conservation of momentum unless you also are thinking about what's on the other end of that rope. But there's one case when conservation of momentum is always the right technique. Does anybody want to take a stab in type in chat if there's something happening in a problem you basically automatically know you should use conservation of momentum? What event is that? Collisions. Yeah, exactly, Jacob. Um, so collisions and explosions. Um, that tells you to use conservation of momentum. The reason is, yes, there should be a negative. Thank you. Um, the reason that conservation of momentum is always the right thing to use in collisions is during the split second of a collision, the forces are so large that um, they're overwhelmingly larger than any external forces you might have. So in a car crash, for instance, the forces between those cars are so big that the external forces are tiny in comparison, and you can always use conservation of momentum. So if you're trying to decide whether conservation of momentum is appropriate, pretty much, like on exam problems and so on, if it's a collision or explosion, it is always the right technique, and in general, you're not going to be using it in other situations. Um, so Jasmine, does that help out with um, thinking about external forces and how they apply to the conservation of momentum? Good. Um, so the energy stuff I have deferred to my example. Are there any other problems people would like to talk about or homework problems that you would like hints on? Ah, Haben asks for question 6. How would I find the angle the father and mother make after they collide, since the final velocity they are traveling with is unknown? Um, so in this problem, you might be saying, well, you have too many unknowns. You have like an x and a y component of final velocity. But in conservation of momentum, right? So most generally, the way that you would write conservation of momentum is that, whoop, I don't want the box tool, I want just the drawy tool. You'd say something like this, initial, plus m2 v2 initial. You know, maybe you've got 3 objects. So you set initial and final momentum equal, right? But this is a vector equation. Energy is not a vector, but momentum is. So since this is a vector equation, I can spell. This applies separately and independently in x and y. So you have one of these in x this is not a vector anymore. Maybe you have more objects. Equals m2 v2x final plus m2 v2y final. And then again in y, you have another copy. So in this case, you've got, conservation of momentum in x and y, and those will give you the x and y components of the final velocity. So you're going to get, some final velocity vector, right? V final. But you can use the same trigonometry that you've always used. To figure out its components. Does that help, Eben? Okay, good. Any other homework questions? Is it usually appropriate to set work to kinetic energy and then add or subtract whatever work other forces are doing? We will see an example of this, so I have a work energy example prepared coming up, but the work energy theorem is work is the change in kinetic energy. So the form is the initial kinetic energy plus the work done by all forces equals the final kinetic energy. So when you're saying setting work equal to kinetic energy, what really work is the change in kinetic energy. So this is where you should start. If you've got forces associated with a potential energy, then this will become instead initial kinetic energy plus, just changing colors here, initial potential energy plus the work done by other forces, so not the forces that you're associating with the potential energy, equals final kinetic energy plus final potential energy. So you've got two forms of the work energy theorem that you can use. One of them where you think about the work done by all forces and don't worry about potential energy. And then another form where you say, all right, I'm going to associate certain conservative forces with potential energy, and then the work term contains only those that are left. And we'll see that example coming up in just a moment. Any other questions before I move on? So Grace asks, so conservation of momentum has to do with existence of external forces. We just talked about that. And energy conservation has to do with whether there are any new energies existing. Yes, in a way. So if you're thinking about whether or not you can use conservation of energy and or the work energy theorem, so you use the work energy theorem when, let me make a guideline here. Let me just kind of clean this up since this is going to be posted. So this is the plain work energy theorem, and this is the work energy theorem with potential energy. So in general, you can use we'll say use energy methods when you don't care about time you have clear before and after states, and the one that I think Jasmine is getting at you can account for the work done by all forces. Let me get the other question. So Renji wants to do problem 3. I'll grab that in a minute. What are these subscripts? Those are just initial and final, Asul. Are you having trouble seeing the colors that I'm using, or is my handwriting too messy? Samantha, yes, I have a work energy theorem problem that I want to do in depth, and that's the next thing on the slides. Like I've got one planned to do this. Renji wants to do problem 3 on the homework. So problem 3 on the homework is 2 parts. Let me grab another thing to write on. Problem 3 asks you to imagine a something rolling down a track that looks like this. It starts here, and then we're thinking about it here. So Renji, does the are these conditions for using the energy methods met here? Because what we're asked is something like A, let's label these points here. So if this is point A and this is point B, the first part of the problem asks what is the velocity at B, and the second part asks what is the normal force at B. So this is a work energy theorem problem, right? You don't care about time, and you've got clear before and after states. The normal force here does no work. I'll let you think about why. And you can figure out the norm. So getting the velocity at B is a simple work energy thing. And then figuring out the normal force at B, well, you can take advantage of the fact that this is basically a circle and you know its radius. So go back to what you know about circular motion. Renji, does that help? All right. I'm going to move on to my example because Samantha's asking for that. So I have lots of questions here where I'm going to be asking you all for input, like you do with your little colored cards. So let's turn on this. So tell me about the work done by this spring. If we draw a close-up of what's going on in this little sled launcher, initially we've got this thing compressed, and it's compressed some distance d. And in the end, oops, this thing's going to uncoil, stretching itself out to its equilibrium distance. There. So tell me about the work done by the spring in that motion. For people following along on YouTube, I'm going to switch to the next video now. I should have done that a bit ago.